We hear it all the time, right? Oil refining is an incredibly emissions-intensive industry, one of the hardest nuts to crack when we talk about decarbonization. But why? To really get to the bottom of that question, you can't just look at the surface. You have to go deeper into the fundamental chemistry and thermodynamics that govern the entire process. So in this explainer, we're going to do just that. We're going to dissect the specific chemical reactions and the energy balances that define refining's intrinsic and kind of unavoidable carbon footprint.
Here's the game plan for how we're going to break this all down. First, we need to define our terms. What does hard to abate actually mean in an industrial context? Then, we'll dive into the two main culprits behind the emissions. First, the massive, and I mean massive, need for high-temperature heat, and second, the chemical necessity for hydrogen. After that, we'll get into the real nitty-gritty and deconstruct the chemistry of how that hydrogen is actually made. And finally, we'll bring it all together to quantify the industry's total carbon footprint. Okay, so let's lay our foundation. Before we can even talk about the specifics of a refinery, we have to understand the difference between different kinds of industrial emissions. This brings us to a really critical concept, something called process emissions. Grasping this idea is absolutely key to understanding why some industries are just fundamentally more difficult to decarbonize than others.
So think about it like this. On one side, you have sectors that are relatively easy to abate. Their problem can pretty much be solved by just switching out the energy source. The classic example is an electric vehicle. You power it with a grid that runs on solar or wind, and bam, its operational emissions are gone. But on the other side, you have the hard-to-abate sectors, and this is where refining lives. Here, the emissions aren't just from the energy you use. They are baked into the core chemical transformations themselves. The CO2 is literally a byproduct of the reaction you need to make your final product. You can't just unplug it from a dirty grid and plug it into a clean one. It's a much tougher problem.
All right, let's tackle the first pillar of why refining is so energy intensive, and that is its absolutely profound demand for heat. I mean, we're talking about brute force thermal energy on a staggering scale. To really visualize this, you can think of the refining process as a kind of temperature ladder. With each major step you take to process the crude oil, you have to climb higher and higher up this ladder, demanding a huge escalation in heat. So our journey starts at the bottom of the ladder, in the atmospheric distillation unit. Now, raw crude oil is this complex cocktail of all sorts of different hydrocarbon molecules, and they all have different boiling points. To even begin separating them, you have to heat the entire batch of crude oil to around 350 degrees Celsius. That's the energy you need to vaporize the lighter stuff, things like naphtha, kerosene, and diesel, so they can rise up and be separated out. But what about the really heavy, gunky stuff left at the bottom? These are huge hydrocarbon molecules with boiling points so high that if you tried to boil them at normal pressure, they'd just break down and turn into useless coke. So what do? You climb up to the next rung on our ladder, the vacuum distillation unit. By sucking out most of the air and lowering the pressure, you lower their boiling points. This is a neat trick, but it still requires you to crank the heat up even further, to around 425 degrees Celsius, demanding another massive energy input from a furnace. And that brings us to the very top, the apex of this thermal challenge, the delayed coker. The final, heaviest gunk from the bottom is fed into a furnace and heated to over 500 degrees Celsius. This insane temperature provides what's called the activation energy to literally crack these long-chain molecules, to snap their carbon-carbon bonds and break them into smaller, more valuable things. So you see, every single step up this temperature ladder directly means burning more fuel, which of course means higher and higher CO2 emissions. So heat is a massive part of the emissions equation for sure, but it's really only half the story. The second and just as critical factor is the refinery's enormous chemical demand for hydrogen. This need for hydrogen becomes especially severe when you're processing the heavier, lower quality crudes, what the industry calls sour crudes, because they're full of impurities like sulfur that have to be removed. Now, just take a look at this table. It details the pretty extreme conditions inside these hydroprocessing units. In processes like hydrotreating and hydrocracking, you're reacting hydrogen with oil fractions at incredibly high temperatures and pressures. This does two main things. It removes impurities like sulfur, and it breaks down large molecules into smaller ones. But look at that final column, the hydrogen demand. See how it just skyrockets as the feedstock gets heavier and more complex? We go from needing just a few kilograms of hydrogen per cubic meter of feed to needing dozens. Let's just pull out that biggest number to let it sink in. A high-pressure hydrocracker, one of the most powerful units in a modern refinery, can consume up to 45.6 kilograms of hydrogen for every single cubic meter of oil it processes. That is a massive, continuous chemical input.
And it leads us to the next very logical and very critical question. Where on earth does all of this hydrogen come from, and what is the environmental cost of making it?
And this right here brings us to the absolute core of our analysis. To really get the full picture of a refinery's emissions, we have to dissect the manufacturing process for its most important chemical feedstock, hydrogen. It's inside this process that the whole hard-to-abate nature of this industry really comes into sharp focus. The workhorse process, the method used all over the world for making hydrogen on purpose, is called steam methane reforming, or SMR, and it's pretty much what it sounds like. The main ingredients are methane, which is the primary component of natural gas, and steam, which is just water heated up to a high temperature. So let's look at the first and most important chemical step. This is the reforming reaction. You take one molecule of methane, CH4, and you react it with one molecule of steam, H2O. You do this over a catalyst, usually nickel-based, at very high temperatures. And what do you get? You get one molecule of carbon monoxide, CO, and 3 molecules of our desired product, hydrogen, H2. But the thermodynamics of this reaction, well, that's where the challenge begins. And here it is. This is the crucial thermodynamic point. The reaction is what we call strongly endothermic. That positive value, plus 206 kilojoules per mole, means that this reaction doesn't release energy. It sucks energy in from its surroundings. It's an energy sink. So to keep the reaction going and push it toward making more hydrogen, you have to constantly pour a massive amount of heat into it. Okay, so that first reaction gave us hydrogen, but it also gave us carbon monoxide, which is toxic and not very useful. So we employ a second reaction to clean that up and, hey, get even more hydrogen out of the deal. This is called the water-gas shift reaction. We take that carbon monoxide, react it with more steam, and we produce one more molecule of hydrogen. But look closely, what else do we produce? One molecule of carbon dioxide, CO2, and this is critical. That CO2 isn't from burning fuel. It is an inseparable stoichiometric byproduct of the chemical pathway to get our hydrogen. So now that we've laid out the two key reactions, we can pause and pinpoint exactly where the carbon dioxide emissions are coming from in this whole SMR process. It's not as simple as just burning gas. Let's break it down. There are two totally distinct and unavoidable sources. Source one is from combustion. Remember that endothermic reaction that needed plus 206 kilojoules per mole? Well, to supply that energy, you have to burn fuel, usually more natural gas, in a giant furnace to heat the reactor tubes up to 800 to 1,000 degrees Celsius. That's your combustion emission. But then you have source two, the process emission. That's the CO2 molecule that was born directly from the water-gas shift reaction. This second source is chemically locked to the hydrogen product. You can't make the hydrogen this way without making the CO2. And we can actually quantify this with some basic chemistry. The overall reaction is 1 methane plus 2 waters gives you 4 hydrogens and 1 CO2. Now, if we look at the molar masses, 4 moles of hydrogen weigh about 8 grams, but that 1 mole of CO2 byproduct weighs 44 grams. So just doing the math, that gives us a theoretical absolute minimum emission of 5.5 kilograms of CO2 for every single kilogram of hydrogen we make. That's the best case scenario just from the chemistry. But then when you add in the emissions from burning fuel in the furnace, the real world number balloons to between 8 and 12 kilograms of CO2 for every kilogram of hydrogen produced. Now let's tie this all back to the refinery. Remember our hydrocracker? Let's say it's using a typical 30 kilograms of hydrogen for every cubic meter of oil it processes. Well, if each of those kilograms of hydrogen created, say, 10 kilograms of CO2, that means the hydrocracker is indirectly responsible for an additional 300 kilograms of CO2 emissions for every cubic meter of oil it upgrades. That is a staggering hidden carbon footprint, coming entirely from the production of its chemical feedstock, and it's chemically inseparable from the process of making high-quality fuels from low-quality crude. Okay, so we've broken down the two main drivers, the intense demand for heat and the built-in CO2 for making hydrogen. For our final section, we're going to put all these pieces back together. We'll synthesize these factors to quantify the total carbon intensity of an entire refinery and see how that number can change dramatically. This chart really tells the whole story. What you're seeing is the refinery's overall carbon intensity, how many kilograms of CO2 it emits for every cubic meter of crude it processes. And look at the difference. A simple refinery running a light, sweet crude might be down around 63 kilograms. But a complex refinery designed to handle heavy, sour crude can be all the way up past 450 kilograms. That huge gap is a direct result of everything we've just talked about. Those lower quality crudes force the refinery to rely on its most energy hungry and hydrogen hungry units, like the cokers and the hydrocrackers, driving the emissions through the roof. So, the main takeaway here is pretty clear. The emissions from both the extreme heat and the hydrogen production are, in a very real sense, thermodynamically and chemically locked into the process of converting low quality crude oil into the fuels we use. And that reality really frames the fundamental challenge this industry faces. It leaves us with one final and pretty critical question. Knowing all this, knowing about these inherent constraints, what is the future role of petroleum refining in a world that is trying to decarbonize? Answering that question properly requires a deep understanding of the very chemistry we've explored today.